It's audible, I think.
Yeah, you are quite audible. How about me?
It's fine. Deepak, just check it out also.
Yes, sir. I checked. Everything is okay now.
It's okay. So that's fine.
Yes.
Right.
So Deepak,
So,
yeah. How many
this is the first session
participants?
today, this morning, right?
Say it again.
Pardon?
Deepak, your voice is not very much clear.
So around 40 students are
Okay, joined already.
are online on right now.
Okay, right now. So I think we can start it right now, or sir? Yeah, we can start it. Okay, okay, that's fine. So very good morning to everyone. Today we have Professor Apoorv Sharma from IIT Roorkee, and he's going to talk about microwave energy, how to utilize in manufacturing, or you can say sustainable manufacturing towards it. And he has a vast experience. Now I request Ms. Kiran just introduce her formally in the class.
Yes, sir.
Yeah.
Good morning, everyone. On the behalf of organizing committee for this FDP program, we would like to welcome Professor Apoorv Sharma and express your gratitude toward him for sharing his knowledge, experience, and wisdom with all of us today. The broad area of his talk would be around advanced and microwave technology in manufacturing. Professor Apoorv Sharma has joined the Department of Mechanical and Industrial Engineering at IIT Roorkee as professor in January 2006. He did his PhD in field of microwave glazing of plasma split ceramic composite and their characterization from IIT Madras in 2003. He has a professional experience of 15 years at various positions at IIT Roorkee. A new approach called microwave glazing has been proposed for the post-processing of plasma spread coating. He has an expertise in the field of advanced manufacturing methods and surface engineering. He has contributed more than 100 publications in international journals, books, chapters, and conferences. He has supervised 14 PhD programs and 18 other are in progress. He has filed 10 Indian patents, 5 of them already has granted. He has been awarded with DAD Research Fellowship under Faculty Exchange Program in 2011, Federal Publication of Germany and National Merit Scholarship Government of India. Now with these words, we would request Professor Apoorv Sharma to kindly take the session so that we all can benefit from this lecture. Thank you, sir. Please continue.
Thank you, Kiranji. Thank you, Kasimji. Thank you so much. Good morning to all the participants, all who are listening to this particular session. So I'm very delighted to be with you, although virtually. Fine, this is the order of the day. Otherwise, I'm sure I would have been physically there had the situations been okay, right for everybody. In fact, in the past, I went there, I met the people there. It was a wonderful experience. And this time, let's see how it goes virtually. So this is also in a way, I try to see the positive side of this altogether pandemic or disaster. So globally, yes, we have faced a lot of hardships. We have faced a lot of problems. People have suffered. Many lost their near and dear ones. That's fine. So means all those things we have accepted. Like it is fact. But few other things, like if we see the positive side, this is one of the positive sides. Now, this technology has taken us or brought us in such a way that wherever you are sitting or you are, so it is practically, it's immaterial. So we can get it connected. We can, even though we are sitting at different parts of the world, so we are interacting, we are conversing, and all these type of activities, teaching, learning activities, like intellectual activities, all these things are going on. Rather, going on in a different scale. That is what I would like to mention. Say, for example, earlier we were managing in our institute, we were managing most of the PhD thesis examiners are from India only, not most, all. And there was a situation that if someone rarest of rare, some examiner request for like Viva VOC through virtual mode, through video conferencing, it used to be a big issue kind of things. There should be approval, proper approval, and approval also will be whether it will be granted or not. That is a big thing. That's why I'm telling it's a rarest of rare. And today it's totally opposite is the scenario. If someone will have to come to the campus physically, he or she needs to be granted permission to enter into the campus. And in that process, what happened, now we have, why India? Now we have examiners for PhD from US, Canada, Australia, wherever you are, Japan, Germany. So wherever you are, or he or she is, he can be the examiner, and he is, and the process is going like this. So now our scholars, our faculty members, they have the equal opportunity to interact with the eminent academics globally, irrespective of their countries or places, and that too without having traveled to this institute. And that's the thing. So this is a kind of, I see the positive aspect of it. So that way, similarly, although I personally, I would have loved to come to Professor Kasim's place. That's a very okay, familiar place for me. I love to come to that place, but for some other engagements, etc., many times it doesn't match. Like today also, like after 1 hour or so, I have another 2 hours, 12 o'clock exactly, I have another meeting. So probably I would have to request Professor Qasim that can you reschedule or on another day or something like that. So these are some of the positive aspects. Anyway, so that's not my talk of the day. So Professor Qasim will not okay, like to hear me all those things. Okay, probably I have to go to my business, for which I have been okay, given this opportunity. Thank you, Professor Qasim, for giving me this opportunity. I would like to share my presentation, and then we will go, right? Is it visible? Hope my presentation is visible.
Yes, sir. Yes, sir.
Thank you. I will call them. Sorry, just I forgot to take my light pen, so now it's fine. Okay. Yeah. So this will be the topic for my talk for next 1 hour or 1.5 hour in this morning. So as Professor Murtaza has given you some inkling, so I will be talking about microwaves. So microwaves, my application of microwaves rather. Although application of microwaves, it's quite old. Okay, it is there for like maybe around 70 years or so in use. But microwaves in material processing, that's not very not very old. And that too, material processing for engineering applications. Okay, probably material processing also there for other than non-engineering applications. It is there, non-engineering applications. So it was there from since long, but engineering applications, or you can say industry applications, so it is very limited, very limited. Only maybe 1980 or so. So there were some okay, the applications picked up and people started using these microwaves for various industrial processes or engineering applications. But the question is, why microwaves? Why microwaves? Okay, so probably I will try to give you some reasoning which will probably make you convinced that yes, microwaves, at least microwaves, they do have a very good potential to be used in industrial applications or engineering applications. And although in the process, I would like to see or show you how it can help in sustainable manufacturing, how it can be like energy saving processing mode or processing tool or time saving processing tool. Okay, so both these two aspects, energy plus time, both are very important, particularly in today's context. Okay, so we'll try to see that. And just give me just let me tell you one thing. These microwaves, probably like most closer, you can say, if you have a closer look of this microwave processing, it will probably come nearer to like laser processing in terms of like effects. Okay, in terms of mode of processing, in terms of to some extent like how laser does work. Okay, in those aspects. But like precision wise or other aspects, okay, lot of things to be done. So it is like beginning of the research, you can say, because as I said, like in material processing itself it is late, and then industrial use and engineering use it was even late. Okay, and out of these things, few contributions we have also tried to make in this field. And therefore more and more resources will bring this process closer and closer to industry adoption, right? Now, as I said, today's priorities are E plus E. Okay, so energy plus time. So we are looking for energy everywhere. Okay, there is a sort of crisis, like as you can see, processing, or you can see the cost of energy, like fossil fuels. Okay, how the cost is increasing. Okay, their cost of production is increasing, their extraction is becoming costlier and costlier, and the source is like limited, right? And therefore people are looking for more and more new energy sources in the form of which are naturally available. So naturally available is the best is, say, one thing is solar. I should not say best, but in terms of like quantum of energy that is available. Okay, so it is enormous. Then people are trying from wind energy. People are trying from say tides. Okay, then there are like this number of so hydro is already there. Okay, so these some of these things, like people are trying more and more like to explore so that we can like become, or we can go more and more sustainable approaches. We can adopt more and more sustainable approaches. So in this energy crisis, probably if we can have some energy sources where actual energy, whatever the energy is being used, actual energy is only 1/10 of the energy in the other conventional sources. 1/10 of energy. Probably that energy will be sort of that we are producing energy. It is a sort of, I'm talking. Although all of us, we know energy can never be destroyed or can never be produced. Okay, it is only like you can say transformation from one form to another form. Now here what is happening is for say processing 1 kg of material, 1 kg of material, whatever the energy you are like in the conventional mode you require. If I use another source which requires only 1/10, then is it not something like this? That we have one we have spare energy, 9 times energy we have spared from processing some other materials. So it's a kind of we have saved 9 times of energy what I would have otherwise spent. So therefore, it is always there how to get a new energy sources, where to get kind of things. But what like from an engineer's perspective, what we are trying to see is, can we do something like this? Can we reduce the energy requirement for processing the same material up to same condition? It is not that I'm talking about half cook things. Calculating half energy required for half cooking is nothing. So it's meaningless. So same material processed up to the same condition, but using a different source of material, different source of energy, which requires 1/10 or say 1/5. Even if it is 50%, it is a big gain in terms of energy requirement, right? Similarly, this now people are like running like anything. After this, I want to do this, I want to do that, I need within this half an hour, I need this within 10 minutes. Like we don't have time for even taking a cup of tea very coolly. While taking the tea itself, 10 different like phone calls will come, and we may have to attend this, that. Like sometimes it happens that without finishing the food itself, one is running. So I mean, we don't have time. We don't have time. Now in this case also, if the same can be say 1/10 or whatsoever, or 1/5 or half of time, if we can do something, then it will be great. That means my processing time is getting reduced, and there I score an advantage. How do I score an advantage? Nowadays, like most of the people, most of the business houses, they are like running neck to neck competition, and they are trying to make the things available to you, be it service, be it product, available to you at the earliest. That's the competition. So if say you are looking for say 4-wheelers, if one dealer says, sir, I will make this model available to you in the next week, another dealer will say, sir, why next week? I will give you this week itself. So is the case with like other. You go to market, you go to like e-market. E-market. Everybody is in the race. Somebody is giving you time on like a date as 12. Somebody will give no, we will give on 10th. So this is a race, big race, and if you win this race, as far as your production is concerned, as far as your capability to provide the service is concerned, then it's great. You will score high. So what I would say is, I would like to say is, microwaves are capable of giving both these advantages to the entrepreneurs, or to the scientists, or to the industrialists. Okay, then if both these can be obtained by using this particular technique, so it helps me being sustainable. It helps me being competitive in my business, right? So with this background, say probably let me explain you few things which, with the help of some data published by others, and there are some data from my own lab, right? So if we see like why we need to be resource efficient, or why we need to be like energy, like saving energy. So if we see the requirement, energy consumption, okay, 1 lakh for or 140,000 terawatt hour, okay. So this energy, so in that, like what are the contributions? Okay, if we talk about 100,000 terawatt hour, so here at present it is like crude oil is there, okay, coal is there, okay, so it is something like that. But as you know, this fossil fuels, the reservoir or the reserves are limited, and the rate at which we are going, see, from 1800 to maybe 1900, see the rate, very, very slow. Then from 1800 to 1850, probably it is a bit high. The slope is a bit high. Then 1850 onwards, you see the slope. So this theta 1, theta 2, and then theta 3, okay, theta 3. So these are, if you see, in this scenario, so probably we won't be able to sustain it with our whatever available energy. We won't be able to sustain for long. It's already, you see, it has crossed this okay, energy requirement. So therefore, it is always like advisable, or it is very important to look for some more energy sources, okay, which can give you processing advantage in terms of processing time, as well as the energy requirement. Okay, let's see. In this, if you see, like of course, all these things are data are taken from some sources, as you can see. So I have taken these data. These are not my data. I have given you the references also, okay, taken from some other sources. So here, if you see, like industry, this is industry, red is industry. So in these, even today, so we are sitting in like say 2020, 2021. So this is where we are today. So if we see this industrial requirement of this energy is like increasing. If we see from 1970 or onwards, so it is going, and this bandwidth is increasing for industry use. So is with other like sectors also, like say for transportation also, for buildings also. So it is increasing. That means, so this is high time for us to look for some sources or some other alternative energy sources which can give us energy advantage to make the world sustainable, or manufacturing activities, industrial activities, okay, to sustain. We need better and better energy sources which can be used more efficiently. Okay, if you see country-wise also, like developing countries like in India, so it is increasing. Almost all it is increasing. Okay, all it is increasing. But if we talk about particularly about India, so this bandwidth is also increasing. Ours is a very big country. Ours is population wise, we have, okay, 1.3 billion population now, roughly. So that's incredible. And if we calculate energy requirement per head, so in this country, so it is huge, really very huge. So therefore, if we can have some techniques which will reduce energy consumption, it is always, okay, better for our sustainability, right? Then if we talk about manufacturing, only manufacturing, then also you see, out of this 100%, manufacturing alone, 40 plus 30, 70%, like is its requirement of manufacturing, around 70%. 70% is in this decade, means the previous decade, and it's going to remain same, say almost, this is again 70%, even as the projected figures of 2040 says. Projected figure of 2040 also says 70%. That means the manufacturing activities, so the energy requirement is not coming down, and therefore it is very important to see that we try to, or we get the energy for manufacturing activities sufficiently in future also. And that is where our need for getting better and better processes or better and better sources very important. Now, if we talk about energy requirement in manufacturing, okay, so material processing, so for doing anything, so to do some work, we need some some energy, some form of energy. If we do by hand, so our body is giving that energy, okay, and to body we fill the that energy sources by taking some food, same thing. So in whatever the form we take energy, so somewhere, somehow there should be some source, and that energy will be required, okay, for doing several work. And in manufacturing, one of the very important way of using energy is interaction is with heat. Say most of the manufacturing activities, like say, okay, casting, welding, then different say heat treatment processes, then say hot forging, okay, then all these processes, they need heat during their material processing, and that requirement is huge, as I said, okay. So that requirement is huge. Now, if our target should be how to bring down that requirement, or how we can fill that requirement with less supply of energy, right? So thermal energy based material processing techniques depend on effective heat transfer, so that is always there. Then in this heat transfer, so there are two effects, like grains of the materials, okay, so they are getting affected, and then accordingly, if the grain size changes, okay, earlier probably it was coarser grains, now it has become finer grains. So in that process, there will be the microstructure changes, and there will be corresponding property changes. Or reverse may also take place, from coarser, finer grains to coarser grains. That we can do always by suitably adjusting the conditions, material processing conditions. And then if the microstructure changes, then the possibility is mechanical properties always get changed, okay. And therefore it is always like a kind of it requires a lot of analysis and a lot of thinking before going to use any sort of energy in this, or any sort of processes which involves heat. Many of you might have seen EDM, etc. EDM is a process, or LBM is a process where which these processes are used for making holes in different materials, or machining, you can say, okay, machining. But then if we very attentively, if we examine that material nearby to that hole, so there will be heat affected zone, okay, which is undesirable. We want a hole. We don't want to spoil the material around that hole. So therefore, that means that microstructure and mechanical properties around that hole, say we want to make a hole here, this piece, okay, but then you will find nearby this material is also getting affected. Okay, so this we call in our terminology. This is we call as heat affected zone. This heat affected zone. Okay, so that means this is mechanical properties of this zone is changing. Microstructure is changing. Okay. Now our idea will be like how we can minimize this zone. It says Z. It should be okay. If not 0, we should try to make it 0. So smaller the HZ, better is the product, or you can say better is the output. Now, some processes like laser and all, although this is there, it is very limited, very small, this HZ. But some processes like EDM and all, like EDM, it is the HZ is very, very high. And that's how the process is, in some cases, that process is not preferred. Okay. It's a one kind of, you can say, limitation of the process. So therefore, what people know, people wish to know is, can we have a process which will have lower or negligible, almost negligible HZ? Okay, where this microstructure and mechanical properties, a loss of microstructure or loss of mechanical properties will not be a major issue, right? So this is one of the objectives of our work also, but at this point of time, our success is limited. So people are working, we are working. I would love to invite you to work in this field. So please start work, and then probably you will get but you will get always better results. Okay. So people are looking for efficient processing. As I said, we don't have time. We don't have we have limited energy. We have very limited time. So we want efficient processing. So therefore, machine wise, or the equipment wise, or the source wise, everywhere, the persons who are involved in these processes, so everywhere we need efficiency. And in one of as one of the examples of this, so probably will be I will be talking about energy and time efficiency here. Energy saving, as I said already, time compression, already I have told. So we are looking for these two here, energy and time. Safety during processing, it is irrespective of any process, it is required. Therefore, you might have seen in the laser work centers, wherever laser processing is there, they will put some warning, okay, some warning labels will be there, or warning posters will be there, that this is the danger zone, so please don't enter without protection, or something like that, okay, or be careful while entering into this, and so on. So processing is processing safety is it is irrespective of the process, it is required. And in the processes like where energy sources like laser or microwaves are used, okay, are involved, there one will have to take extra precaution for this safety. Okay, these are essentially different sources of energy, which has got different characteristics, which works in a different way, and therefore one needs to take care of those things while working with laser or microwaves. Then environment-friendly processing, this is also another thing. As you have seen laser processing, so on-site, it is very, you can say, environment-friendly. So no smoke, no heat will be, not much heat will be radiated, no smoke will be created otherwise, and so on. So that's a plus point of working with laser. So is with microwave. No on-site heat will be produced, no on-site smokes will be produced, and so on. So these are some of the advantages, and that contributes to the environment as such, like at the site of where this material processing is going on. But of course, if you ask me, is it safe or is it always environment friendly, then probably always means it is there. So we are using this microwaves, or for laser, we are using electrical energy. And yes, we will have to admit that wherever that electrical energy is being produced, okay, somewhere, so probably some carbon footprints are being created, okay. And if it is purely natural source like hydro energy and all, it is pretty less. But if we are using others like fossil fuels, then carbon footprints that are being produced is relatively high, right? Then quality product. This is another important thing. Nowadays, people have money. They are ready to pay, but they want in return, they want quality. So money they are ready to spend. Even for a phone, see, for a phone, I'm not talking about for everybody, but why do we need a phone? Say, okay, now it has become a kind of multitasking device, but earlier we need only for talking or for sending a message or some mere kind of communication, okay. But for that, maybe 5,000 or 5,000 rupees handset also will work, and 50,000 rupees handset also will work. 5 lakhs or 1 lakh handset will also work. But people are spending money on that. Okay, they are putting more money or spending more money, provided they get better quality product. Okay. And in this, as I said, here, mechanical properties are very, very important. So what if my energy consumption is very less, but while doing the work, I have lost the mechanical properties of that part, or the part is no longer useful or not good, or I'm using 50% energy, that's fine, but it is taking double the time of processing time in a conventional mode. Then also it is, you can say, it is not useful, right? Therefore, quality product, as well as energy efficiency, as well as time efficiency, all these things need to be taken care of while using for producing, say, a product or services, right? And in this, I'm very happy to share with you that if you use microwaves, okay, for material processing, many a times people have reported that that quality improvement is there. Quality improvement is there. That means with microwave, you can find energy efficiency, you can find time efficiency, as well as you can find quality, better quality. Now, if all these things are there, three important aspects are getting satisfied, or it has the potential to satisfy all these three major requirements, then probably it is worth going for or looking for a process which we can say, like, yeah, could be a sustainable, okay, process solution to this. So as I have already said, so for all these like requirements, if we talk about, if we ask what we can look for, what's next for this, which can give me the solution for energy, which can give me solution for time, which can give me solution for quality. So probably microwave may be the answer. And how this is not a probability but a reality, that I will be showing through some data, my own data, and data being published by other people. Right? Fine. So some developments I would like to show you, okay, and some of those are from IIT. Professor Murtaza?
Yes, sir, please.
Okay. So it's fine. Everything going fine?
Yes, sir. Everything is
I'm
going
audible.
fine.
Okay.
Yes, sir. Yes, sir.
Right. Thank you.
Yeah, thank you, sir.
So yes, already I have told about energy efficiency, time efficiency, then safety, environment friendliness, then reduction in material loss during processing. This is another factor. So that is also done. And then near net safe manufacturing. This is also another aspect. Like you do not need a secondary processing after this in most of the cases, right? So that is also that also helps in like energy saving, as well as like cost saving, time saving. If in one go you can have near net safe product, then you need not to go for secondary processing, which involves time, energy, then handling, material handling becomes okay or gets reduced. So all these things are very, very important. As far as time efficiency is concerned, if you try to see this, just here is an example. So red is microwave heating, and like blue is conventional heating. CH is nothing but conventional heating. Okay. So for the same material, say this is stainless steel. 316L is a stainless steel. 434L is stainless steel. So for processing the material, same material I'm talking about, what is the like exposure time required for conventional heating? This is conventional, and this is microwave. Okay, red is microwave. If you see in each and every cases, if you see this, what is the statistic says? So almost all cases, in these cases, so this is 450 and this is something around 50. Okay, so almost 9 times, or 1/9 or 1/10. So every case is 1/9 or 1/10, 1/8, 1/5. So this reduction is there. Reduction is there. Reduction in energy. For, of course, I'm talking about the same material. Same material. There is no point in comparing two different materials, but these are the data for same material, and these are not my data. These are, I'm giving you the references as well. Okay, so all these have been collected from these publications. So that means the people have like worked on this, and they have reported on the various materials which are having industrial relevance. I'm not talking about non-engineering material processing. That's what at the beginning, as I said, microwaves may be in use for last 70 years or so, but many a times it is for non-engineering use. Even today, almost like every modern kitchen has got one micro oven. Every modern kitchen, micro oven. But then that micro oven is used for what? Microwave oven is used for what? So microwave oven is, so that is used for material processing. Which material processing? Only food material processing. Food material processing. Okay. So this is non-engineering material processing. But I'm talking about here whatever I'm giving you is like engineering materials. These are used for various industrial processes. And here we have found like energy requirement is 1/10, 1/5, or half, or whatsoever, like that. So this is incredible. Oh, sorry, this is time requirement. Sorry, I'm talking about time. Okay. Similarly, for energy also. Now let us see the energy requirement. Okay. So power consumption. So power consumption in kilowatt. So this is in kilowatt. In one case, it is almost like 6 kilowatt, and in one case, it is like 1 kilowatt. Okay, so it is something like in the first case, it is like almost 1/6, and all other cases, if you see, so it is probably half. So it is probably half. It is something around half, 50%. So energy requirement is very less, and all these data are again, okay, from these sources. So people across the world, so they have worked on this and they have published this. And if you see these materials are again engineering materials. So that means I'm not talking about non-engineering materials processing. So microwave heating is red, and if you see everywhere, this is red is okay. Less. So this establishes this type of like data, like established. That's what I told at the beginning. I'll try to show you some data, and with those data, I will try to convince you that microwave has got better, can say, possibilities or better opportunities to be used in industrial use, which can help us in achieving energy sustainability, or like time. Okay, achieving better processing time. Just like, let me give you one more example here. So this is again, this is okay, published data, not from my own data. So here the material is same. As you can see, the material is same. Material is same, and we are trying to hit this material, say, up to 1500 degrees Celsius. Up to 1500 degrees Celsius. Same material, same quantity. We are trying with two different processes. One is microwave sintering, and the other one is conventional sintering. Red is conventional, and this is microwave. You see this? Can you see this? So this is something around, okay, 75 or so. That is 75 minutes. Whereas the same material with conventional, it is coming to be something around, say, 300 or 325. And in one case, it is 75. Okay. So it is something around 4x what is required, 4 times the higher time required in conventional processing. This is one of the cases. Okay, I'm giving you one of the cases. And to bring it to the same processing temperature. So this much is that, say, saving in time. If we go back to the first slide where we are talking about energy and energy crisis and time, okay, time crisis. So probably, so this data, this type of data provides you better convincing results. Yes, people have found it out. Scientists have worked it out, and they have proved it that conventional sintering takes much higher time, much higher energy. The same probably same data, same data, whatever we are seeing here. So we are seeing here that it is like time-wise, how less time it is required to achieve that same, say, 1500 degree Celsius or so. 1500 degrees Celsius or so. Now here, if we were talking about the third dimension, about quality, we are talking about E, T, Q, energy, time, and quality. Now, if we talk about the same material, so in the conventional processing, we are getting this type of microstructure. In microwave processing, we are getting this type of microstructure, Now, so you will appreciate, or you will you can map it that. So this is having finer microstructure. And finer microstructures generally, in general, not necessarily always. So in general, tries to give, or in general provides better quality, finer microstructure. So here is also the same thing. Okay, so here it is coarse microstructure, and here it is fine microstructure. Finer microstructure always gives better quality in most of the cases. Now, so what I'm talking about, we are taking less time. We are taking less time, considerably less time. We are taking 1/10 or 1/6 of energy. We are taking 1/5, 1/2 of time for processing, and at the same time, we are getting better quality product also. That means all these EEQ, these criteria are getting satisfied while using microwaves, right? Therefore, so probably I think this much is sufficient to establish the process that yes, it has got better future or better potential to be used in material processing. However, the things are not very easy. It has got its own challenges. A lot of challenges are there, and that is the reason why so it is getting delayed. We do not know much about these microwaves. Microwaves are traditionally from the very beginning, they are being explored for more and more for communication purposes, not for material processing purposes. Okay, therefore our knowledge is limited, and once we do more and more researches, so probably we'll be better. We will have better knowledge, and we will be able to use it in a better way. Then operating condition, power, frequency. So here also it is one more thing. The operating condition you cannot use like welding torches. You bring it to my room, you can do some few welding here. So with microwave or laser, it is not the case. You need a specialized equipment, and you need a kind of specialized environment also. In laser nowadays, you can take it by a few meters using this optical fiber cables. Okay, optical fibers, it is possible. But in microwave, that condition yet to be achieved. So you need a particular environment, particular operating condition within that chamber only you can use microwaves. Otherwise, there are health hazards which I don't advise you to explore. Explore means you getting exposed is not advisable. You explore scientifically how this can be conquered. Okay, Then frequency is also another thing. So we do not have all the frequencies available in our electromagnetic radiation bandwidth. So this is nothing but EM, electromagnetic radiation. So in electromagnetic radiation, again, this is say for microwave. Laser is there, then visible light is there, infrared light is there, say visible, infra, then infrared, then UV, and there are different different spectra are there. So all these they are within certain frequency of this energy, or you can say electromagnetic radiation, right? Within this microwave radiation also, we cannot use all the frequencies. We have some limited 2.45 gigahertz, 915 megahertz, and then 30 gigahertz. This is gigahertz, then 30 gigahertz. Like that, there are few frequencies only are allowed for industrial use. So it is not that tomorrow I can use, so I want to use 3 gigahertz. No, that is not permitted. In this microwave itself, as I said, like they are being used, some frequencies are being used for communication. And in communication also, if you see, some are used for say television communication, some are used for like radio communication, some are used for say defense communication, although it also comes under this only, radio communication only. But in radio communication itself, again, for civilians, there is a different radio communication frequency. For defense people, there are different communication frequencies. And that's the reason why we cannot hear what the defense people they are talking about, or what the other people talking about. Okay. So they will be using very specialized frequencies and very specialized equipment to receive those frequencies, transmit as well as receiving. Okay, so these are some of the challenges. We don't have the liberty to use whatever we want. Another big thing is material dependency. Microwaves, just like that, you cannot use any material for processing just like that. No. I will show you some of the examples. Okay, so with different materials, it behaves in a different way. And if you have purchased microwave oven yourself, you would have seen there will be a big warning poster inside that packet, or outside also it will be written, do not use it for processing metallic materials. That means so as far as that equipment is concerned, so you have that limitation. Material dependency. You can use only few materials which are microwavable. They say microwavable. Okay. And they will give you some materials, some cookwares, etc., which can be put inside that microwave oven. So that is also again a different kind of material which can be put inside the microwave oven, but it will never get affected. But to keep milk inside that pot, the milk will get boiled. Okay, milk will get heated up. If you keep rice inside that, it will get heated up. It will get cooked. You keep meat inside, it will get cooked. But that bowl or that whatever that plate will not get anything. In fact, it will not get heated also. That is the beauty of material dependency with microwave. Okay, you are keeping on a plate, say meat, say potato or whatsoever inside that microwave oven. Potato will get boiled, means there will be lot of heat. Okay, lot of heat. But the plate or the bowl in which you are keeping that, it will not get affected. It will not get heated up. So it's a kind of wonder. Why it happens, that also I will tell. Okay. And they say, do not keep the metallic materials inside. This is another extreme. Why another extreme I'm talking about? Which type of materials do the engineers need or the industry needs? Okay. In engineering, or what we call as engineering materials, so these are mostly metals, alloys, ceramics, then polymers, etc. And unfortunately, these metals and alloys, metals or any metallic materials, so they say don't use inside microwave oven. So that's a big problem. That means as far as engineers are concerned, so probably microwaves are useless for. So that was the kind of turning point in my research interest. So I thought that from the other way around. Okay, why can't we make it work? Why can't we use metallic materials inside microwave oven? So that started, like with that, I started thinking and started like implementing projects and started some manufacturing activities. And today, like you can cook potato or meat inside microwave oven, same microwave oven inside, I can cook steels, mild steel, in Cornell. So I can cook, okay, aluminum, copper. I can cook different alloys, metallic materials, same microwave oven. Okay. So plus, but you please do not start if you are not having much exposure on this. So please do not start straight away going after this lecture that A.K. Sharma sir told he can do it. Why not me? So please don't do that. Before that, try to have some experience with like literature and so on, right? Special requirements. So what are the special requirements? Yes. So if I need to keep that metallic material inside that oven, so I need some special requirement. Okay. If I want to say make the milk hot inside microwave oven, so I need special requirement. What is that special requirement? Probably I need a material or glass which will not be affected by microwaves. If I put in a material like which will also get heated up and everything will get heated up, that means the glass will will also get melted. So that is a special requirement. Okay. So that kind of so tooling requirement. So tooling requirement, like a special requirement is that I'm talking about tooling requirement. Then environment also. Like as I said already, I have told about this environment also. It's like for laser microwave, we need some kind of protected environment so that safety can be ensured. Okay. Then in some cases, now we are doing research. In some cases, we need, say, you can say, noble gas and environment, like say argon gas and environment, or in some cases liquid nitrogen, or in some cases we are using sometimes we are using water, or like that, some dielectrics. Inside that dielectric, we are using microwave machining. So that is a kind of environment that is required for doing microwave processing. So with this, even though all these you can say like limitations or restrictions are there are people who are working for like processing materials using microwaves. Almost, if you see, almost all types of materials are being like processed, like ceramics and ceramic. CMC means ceramic matrix composites. MMC means metal matrix composites, right? Then chemical synthesis also people are using, and it is found to be very effective. Chemical reactions get enhanced. But, like the speed of that reaction becomes very like high. Then rock, cements, etc. Then different materials, medical and drugs, like yes, very effective. Okay, so there are so many things, polymers and polymer PMCs. polymeric matrix composites. Of course, food and drying, it is there in any like kitchen. We have this. However, there are opportunities. Okay, so although we have processing constraints as far as the materials are concerned, as far as like frequency is concerned, power is concerned, safety is concerned, but still there are like ways to do it. Like as I said, so today I can join stainless steel to stainless steel, weld stainless steel to stainless steel, or weld two pieces of Inconel by using microwaves. So that means there are opportunities. It is now my inability to come up with or to develop a device which is something like similar to or better device than that of what is that welding system. If I can do that, probably microwaves will work in that mode also, right? Then target metals, ceramics, polymers, all these things, they are composites, PMCs, CMCs, and MMCs. All these can be processed in this microwaves. Then other materials also, glass and chemicals. Glass we are doing, like we are processing glass. We are working for glass drilling. We are trying. We have got some success. I should not say completely we are successful. Heat affected zone we are yet to overcome. It is becoming a big, say you can say, challenge for us, but we are working. So all these things we have published in this paper in composite parts A, okay, applied science and manufacturing. So this is composite part A, and I'm very happy to share with you that this paper was almost 3 years or more than 3 years. This paper was listed in their journal website as one of the most downloaded, highest downloaded papers. So similarly, so Mitra is my PhD student, so he has already completed. And this is a review paper. It is like a book, mini book, you can say. And this gives you fair amount of information. You can read this paper and you can get some exposure and you can try. Then possible industrial applications, as I said, casting, forming, micromachining, it can be used. Okay, so we have almost we have filed patents in casting, micromachining. We have done that, so we are waiting for some more. Then advanced materials like we have used, composites, cladding, etc. We have developed. Okay, composite joining we have done, composites like curing we have done. All these things we have done. Say bulk metal we have done, alloys we have done. Okay, nanomaterials we have worked with. So for various materials, etc. So we have used it. Now, just let me give you a very brief about what microwaves are. So microwaves are, as I said, they are nothing but electromagnetic waves. They are nothing but electromagnetic waves, but they are orthogonal to each other. One component is electric, the other component is magnetic. They are orthogonal to each other. So if one is in this plane, the other one is in this plane. I will show you. And the wavelength is this, as I said. Frequency range is always corresponding. Or originally used for communication, but later on, this gentleman, Percy Spencer, this gentleman, he has found out that yes, this can be used for material processing also. In fact, he was an engineer, defense communication engineer. He was working in some defense projects, and he was using microwaves for his communication equipment. He was working in a camp where the temperature was below 0 degrees Celsius. Sub-zero temperature he was working. Okay. And while working, he has found that on his table nearby to his equipment, he kept some chocolate pieces and they are melting. Chocolate pieces are melting. Is it not like something very curious to be? Because so he is working working at a sub-zero temperature, and sub-zero temperature chocolates getting melted. So that is sort of unbelievable. And he became very curious with that. Then he, after thinking so many things, then he could find out only one reason for that, that the chocolates can get heated up or getting melted only because of his equipment, microwave equipment. And in that, those equipments also, the equipments were cold, very cold, he found that. Therefore, it must be the signal or that frequency, microwave frequency, which he was using, which would have like caused this problem. Okay, so that's how he postulated that yes, so this is microwaves can be used for heating materials, and so he established it in the year 1950. That's why I'm talking about it is almost 70 years old technology. And he has developed one like microwave oven. So this is the microwave oven. So this was costing something around, okay, say $5,000 US dollar at that time. And nowadays these microwave ovens are found in 50 US dollar also. Okay, so 100 times more costlier. So he was the gentleman who developed this microwave oven, world's first microwave oven for say material heating purposes. He knew that it will work, and he developed it. He got it patented. Okay? And the frequency used is again 2.45. So as I said, so this is the microwave, like so this is electromagnetic spectrum, the whole spectrum, right from visible light, okay, to the shortwave radio communication frequencies. So very high frequency, ultra high frequency, okay. So as you go this side, so this is frequency is increasing, wavelength is decreasing, okay. And as you go sorry, what is that? Yeah, wavelength is decreasing here, okay, and frequency is increasing here. So this side frequency is increasing, and this side lambda is increasing. So that is what is that? Wavelength. So as you know, so this is like inversely proportional, right? And the microwave window is this only 1 meter to 1 millimeter. If you can see 1 meter to 1 millimeter, that window is only microwave window. And this within this 1 millimeter also, only this, if you see 2.45 megahertz, this frequency, and 2.45 gigahertz and 915 megahertz. So these two are the frequencies. So this is in megahertz, okay. These two frequencies are used for commercial purposes, material processing purposes. All others are for some like communication, some other purposes. Okay? And as I said, like there are two components, as you can see in this figure. So microwaves, so they are like in one in blue, one in red, and both are mutually perpendicular. If you can see, they are not in the same plane, they are in the mutually perpendicular. One is in say XY plane, the other one is in XZ plane. Okay, so this is X, Y, Z. So one is in XY plane and the other one is in XZ plane. Now, since these two waves, so electric and say magnetic, so they have different characteristics. electrical component will have different characteristics and magnetic component will have different characteristics. Therefore, the kind of materials when they will like work with, so we will have different effects. Like magnetic material will get affected by these microwaves in a different way. Electrically conductive material will get affected in a different way. In electrically conductive also there are, or in magnetic property wise also, if we talk about, one is diamagnet, one is paramagnet, and one is ferromagnet, right? These three broad classifications are there in all, like if we talk about magnetic materials. Now, these will affect in a different way the ferromagnetic materials. The same like waveform or the same wave will affect the diamagnetic material in a different way. Now, probably you can appreciate why the different material properties like behave in a different way. Why I can't keep that electrically, say steel material or some iron rods inside a microwave oven. So steels have got different electrical conductivity. Copper has got different electrical conductivity, and then like say aluminum has got different electrical conductivity. In electrical material also, if we talk about electrical materials, so they are also electrically conductive, electrically semiconductive, and electrically non-conductive materials are there. And this, if we talk about that electrical component of this microwave, so this will also affect this conductive, semiconductive, and non-conductive materials in different way. Okay, so therefore it is highly material specific. Okay, so the effect will be according to their material characteristics. Fine. So the advantage here or the disadvantage here, just like let me give you one very small example in this. So all these figures are actually not mine. So please remember these are like taken from some sources. I have indicated the sources also. So this is conventional heating. So you keep the material near to the, so this is the source, okay? This is the source, and the heat will propagate slowly, and the entire material will get heated up. So this is a cold material. Slowly the heat is getting transmitted, and the material is getting heated up. Now, by the time this portion of the material gets heated up, this portion of the material gets overheated, and sometimes it may get charred also. Same is the case here. This portion gets heated up first, then slowly like this. But in microwave material processing, it is reverse almost. So it starts, the heating starts at the core first, and it goes out and out and out, as you can see. Okay, so slowly it is coming from inside to out. So this is called outside in, and this is called inside out. So this is in case of the microwave heating. This is microwave. So it is a case of almost reverse. And in most of the cases, this becomes mostly like more and more uniform in practice. So there are other mechanisms as well, like how it gets, the heating gets developed. So I won't spend much time on these effects. Just one, I'll give you that example. Water. So what is water? Water is one H2O, right? So one oxygen atom is, okay, sorry, oxygen atom with 2 hydrogen atoms. So this is being found here, 1 oxygen, 2 hydrogen. Now, as you know, oxygen is electronegative and hydrogen is electropositive. Now, when you like allow microwaves to move through this, because of this electrical component, as we have seen here, electrical components. Okay, when the positive half will come near to this, near to this atom, so what will happen? That negatively charged O will be attracted. Okay, and H2 or hydrogen will be repulsed. And when the next half comes, this negative half comes, so then the reverse will be the effect. Inverse will be the effect. So therefore, this will take place. This will take place 2.45 gigahertz frequency. It is moving. So you can think of what is that? So in almost in 1 nanoseconds, it will have to this reversal will have to take place. This reversal, positive to negative, negative to positive. But because of their own inertia, it cannot follow. And therefore, there will be a lag, or there will be a, like you can say, loss of energy. Okay, which cannot keep up the speed, same speed with that of 2.45 gigahertz frequency. And that causes the heating inside the material. So this I am talking about, I have given the example of water, but there are other mechanisms as well, like conduction losses, dipolar losses. There are so many, like for H field also similarly, for H field also, like magnetic field also, there are similarly like other mechanisms, hysteresis losses, then eddy current losses for conducting materials. Then electron spin. There are so many other things are there. So I don't have much time. So I skip those things just to give you a kind of quick recap of this. That microwaves are being used for telecommunication in this, say 1940 around. Then rubber curing and all these things. So these are you can say some heating applications. So during 1950s and 1960s, mostly food processing was dominating, but some industrial use were also there, not much. Then slowly people, chemistry people, they have picked up for chemical processing, or say plastic processing, say curing, etc. Then ceramic processing. So this 1980s, 70s, 80s, then some serious engineering material processing that took place. And then 1990 onwards, it was extended to more and more materials. And 2000 onwards, so it is getting extended up to metallic materials also. Now, if you see, almost all sorts of materials are getting processed by microwave. So this we have published in this paper again, that composites part A paper. You can take the reference of this and you can look for this paper. We have given everything there. So if you see here, so as far as low temperature processing is concerned, so lot of materials, okay, like say biochemicals, then say paper, cooking for different materials, food, etc. So those are actually low temperature processing, etc. Wood, okay, ceramics, some low temperature ceramics. So we are like we have used these things for that low temperature application, which is mostly synthesis and drying. And during 1970s and say 2000 around, so sintering was mostly dominated material or the process. And there also the microwaves were used, microwave sintering. So sintering, then drilling, then say glass processing, soldering, brazing, for different processes has been used for different materials like carbon nanotube and other materials being used. Similarly, in advanced materials, high temperature, almost all sorts of like oxides, MgO, ZnO, okay. If you see titanium dioxide, alumina is very high temperature, zirconia, very high temperature oxides. So these have been processed. Tungsten carbide has been processed. We have processed tungsten carbide in our laboratory. So in a way, we can say tungsten carbide has got melting point more than 3000 degrees Celsius. So we have reduced that heating effect inside the same microwave oven, which is actually designed for something around maximum temperature is, suggested temperature is 250 degrees Celsius. And we have developed there, say, approximately 3500 degrees Celsius inside that same oven, microwave oven, with the help of some fixtures, etc. I'll skip this. I think I don't have time. So rather, I will give you some examples what we have done in IIT Roorkee. So this is one microwave applicator I am using in my lab. So this is an industrial type, okay, but it has got only capacity of 1.45 kilowatt, 1.45 kilowatt. So we have like vacuum pump also. We can use this. We have like facility to put argon gas inside also, okay, inside this. So this type of facilities, as I said, like environment, we can create different environments inside this that we can do. Then we have one more type, that is, this is actually home microwave oven. So whatever available in the kitchen, so this is like that, okay. And this we have been using for several years. So it is almost like 15 years I have been using this oven for my research. Many PhD scholars, they have got their degrees using this oven. Since 2006, we have been using these microwaves for various processes. One is joining. So we have obtained a patent granted for this. Then we have developed cladding. So we have got patent for this. Then microwave drilling, we have filed patent. So this is a patent with you can say Department of Atomic Energy, DAE, a joint patent we have filed for this microwave drilling for glass material. We have filed that. Then microwave casting we have developed in situ microwave casting. Inside the microwave oven, you can keep the metals block or the bulk metallic materials, and you will get the cast. Of course, you have to keep that mold inside. Okay, so you can get cast. That also we have done. And now presently we are working with microwave sintering and curing. So these things are also we are working. So in a way, so I'll show you some results. So we are getting good results, and therefore, and within very less time. So whatever I'm talking about is that less energy requirement and less time requirement, both are getting fulfilled. And quality wise, in many cases, we are getting almost at par quality. In many cases, we are getting better quality as far as the microstructures are concerned. And in some cases, we are getting bad quality. Bad quality in the sense that we are getting more heat affected zone. Higher the heat affected zone, worse is the quality. So that I must I must tell you, okay, and yes, that is the case. So in those cases, you need more and more resources. Say microwave casting. So this was developed by my student Mishra and me. So in fact, this was like started with a BTech project group. So they did some work, and later on they could not finish. BTech students, they have less experience, and they put relatively less effort in this, but nevertheless they got a good beginning. And later on, Dr. Mishra, now he has graduated, he has got PhD degree. So as a PhD scholar, so he got it developed, and we got a patent for that also. Okay, we have applied for this, and now we are waiting for the final granting of that patent. So we keep inside this cavity, say this is microwave cavity, say you can say this is the microwave oven inside which we are keeping that entire like casting arrangement, and we are getting the cast, something like this. And this cast we have evaluated for a microstructure, proper microstructure or quality, etc. And we have found that quality is even better. Porosity is very less, very, very less, okay? And microstructure is better. Properties are better. So these are some of the, like, we have like characterized that microstructure, how at different locations microstructure can be different, that we have seen. Then these are different casts, some copper, aluminum alloys, okay, stainless steel, some aluminum alloys. This is copper. So we have used this type of things. Then another process is the drilling, microwave drilling. We have developed microwave drilling of glass. These are some of the results. As you can see, as I told you, so there are some heat affected zones. So these are some HAZ. Okay, so here these are some HAZ. Then there are some cracks also that there are cracks. As you can see this crack, as you can see this crack, some cracks are there. So we have got limited like success, but we are trying to make it better and better every day with different arrangements, etc. So we are getting better results. So we have worked on this, and we have published also. You can see these papers, etc., and you can always find out. There's some holes are very good, okay, very good, but some holes are having HZ, if, as I said. So these are not very good. So these we need to like better or improve upon. This is how microwave drilling is done. So this is the drilling zone. This is where the drilling is taking place. And this is what you have seen in my first slide also. That is from my lab. Okay. So joining also we have done a lot of like threading also we have done. We have done joining of mild steel to mild steel, stainless steel to stainless steel, inconel to inconel, stainless steel to inconel, like similar and dissimilar joining we have done. We have patented this also. So I think with this, okay, I would like to conclude this. Already it is time. Okay, so it is for sure that microwave energy can be used for energy saving and processing time saving, as well as the product quality also will not get suffered this much. Okay. So only thing is that we have to keep working. So before I finish, so let me tell you that these.
Thank you very much for a wonderful and vast experience of microwave.
Yes, thank you. Thank you so much.
Yeah. So thanks a lot for a wonderful, this a vast knowledge of microwave. Though we assume that it is only used in the food industry, because we have seen in our kitchen. But Professor Sharma elaborated how they have converted this energy into uh, metal processing or a material processing industry, and how efficiently save the energy as well as further use in the uh, different type of manufacturing issues are there, such as casting, sintering, cladding, and joining processes are there. So I hope that everyone has got a flavor of new new source of energy development in the material processing. And with that, I just, if any queries are there, we are ready to take it up. Professor is with here. Is any query? Deepak?
Uh,
Deepak?
yes, sir.
Yeah,
Dr.
any
B.
questions are
Prasad
there?
is there. He have one query.
Yeah.
Dr. B. Prasad, sir, if you have any query, please you may ask. Please unmute your mic and then please ask. I think he's not there, sir. Sir, please.
Just, do you have his question? So just read out.
No, he just raised his hand. That's why I'm asking. Hello.
Yeah,
Sir,
yeah.
he raised his hand during the lecture. That's why I'm asking.
Right. So just, sir, I would like to ask one thing about the centering processing. Um, is it possible we can control, you can say, porous base centering is there?
Yes, porous base centering we are trying. We are trying to like make some scaffold like for human body.
Right.
This thing, implants. So implants, as you know, like they need some porosities for that tissues to grow inside that. It is like in a single go, it is difficult to maintain the porosity, but that needs again further research. But it is possible to maintain porosity. Okay, and there can be, like, if you remember in one of the slides, I said like it is from inside out. Inside out, that is one of the like heating characteristics of the of microwave heating. That can be very well, that concept can be used for developing like porosities also in that fashion, which is like advantageous for the like scaffold, etc. Okay, but with like this much of parameter, this parameter, say 600 watt, 800 watt, or 1 kilowatt for 15 minutes, I will get like 2% or 10% porosity. That kind of mathematical correlation is not existing. Okay, so that you have to like develop by trial and error method, or better modeling you have to do. So those things are yet to be done. But yes, like porosity control to some extent it is possible at this point of time, but in future it can be better modeled, and with further research it may be possible.
Thank you. Thank you very much. So
Thank you.
actually that I am thinking about, yeah. What? So on the
Right.
behalf of our Atal FDP process program, as well as on the behalf of our mechanical engineering department and Delhi Technological University, with deep, you can say, thanks and regards to our professor, who was the speaker of today's this talk. So once we, yeah,
Sir, I had a question.
yeah.
Please go ahead.
Just
Yes,
do it fast, yeah.
Sir, I wanted to ask, like, what are the advantages of using microwave in casting and drilling?
Casting and drilling, the same advantages you can say, like the energy. Casting is very energy intensive process, as you know, for heating and the melting. So melting of a material which has got melting temperature, melting point of say 1500 degree, 1800 degrees Celsius, that needs a lot of like heat. Okay, lot of heat. But what we have observed here in using microwave, you can get that heating very fast, pretty fast. So therefore, one thing is you have like gained time. With less time, in less time you can melt more. Second thing is, since time requirement is less, usually the energy required is also less. Okay, and therefore both the advantages are there. In drilling, yes, we are yet to establish its superiority over laser. Probably while asking, you are keeping laser drilling in mind. I can probably I can guess. because laser drilling gives you very neat hole, okay, very finer hole, and with microwave we are yet to achieve that. Yes, I do agree, but what is the history of laser drilling and what is the history of microwave drilling? Microwave drilling, we like applied for patent in only something like okay, 7-8 years back. 7 years, oh no, not even 7 years, 2013 or so. Yeah, 7 years back, roughly. And what is the history of laser drilling? Several decades. So, and that means that laser drilling, it has got that perfection, that sort of like precision over sustained efforts of different researchers over this period of time. Several decades, people are working for this. They have perfected this process. They have achieved this much of accuracy or precision. So similarly, we have developed this process, and now if you people keep on working on these, so certainly in near future, people will get better, probably better success and better results. Yeah.
Yes, sir. Thank you so much, sir.
Thank you, sir.
Yes, I
No.
think, sir, so thank you again in the last. We would like to thank to Professor Sharma as well as all the participants. And thanks a lot.
Thank you.
Thank you. Thank you so
So
much.
thank you, sir.
This opportunity. Thank you. I log out.
Now,
Thank you.
yes, sir. Thank you, sir. Now our next session will start at 11:45. So please be online, everyone. Dr. Anil sir is there for the next lecture. Okay. Thank you, everyone.